Hi everybody. So we're going to talk about tangent planes and normal lines in this section. So we have a surface S, right? S for surface, and it's defined implicitly by the equation capital F, right, as a function of x, y, and z equals 0, right? So this is nothing new, right? You've seen surfaces defined implicitly. As an example, you have the sphere, right? So this is the equation of a sphere of radius 9. So you think of your F, right, capital F, as just x squared plus y squared plus z squared minus 9 equals 0, right? So obviously, usually you see it written this way, where x squared plus y squared plus z squared equals 9. But just to be consistent, you can always set it equal to 0. You can just subtract the 9 from both sides, subtract the constant from both sides, right? So yeah, so this is a surface of a sphere, right? So sphere radius 9. So it's defined implicitly, right? And in some cases, you can solve for z, right, to write it in the usual form, little f of x and y. The problem with the sphere is that you're going to have, a plus or minus. So you're going to have plus or minus the square root of, 9 minus x squared minus y squared. So the plus for the top half of the sphere, and then the minus for the bottom half of the sphere. And so for these implicit surfaces, you cannot always write it this way, with z being a function of x and y. Okay, so in some sense, these implicit surfaces are a little bit more general, right? Because these surfaces as a function of x and y, can't sort of fold in on themselves, right? You can't have two z's for the same x, y. Like for a sphere, it fails the vertical line test, right? You have 2 points with the same x and y. Okay, so that's a surface defined implicitly. And then you have a point on the surface and a curve. So let me get rid of all this and draw the surface properly here. Okay, so suppose we have our surface. I didn't mean to make that straight, although I guess it doesn't matter. Okay, so this is our surface S, right? And we're going to denote one of the points on the surface, say right over here. So this point here, P, will have coordinates x0, y0, z0, right? And then we have a curve. I guess I'll do that in red here. We have a curve on the surface, right? So this will be our C. So it's a curve that exists on the surface, and it also passes through the point P here, right there. Okay? So that's the situation, right? And the curve is given parametrically, right? So as a function of t, right? Right? So I can represent any other point on the curve, right? All these points here can be represented on the curve in terms of t, right? In other words, normally it's a function of x, y, and z. However, x depends on t, right? Y depends on t, and z depends on t. So by restricting to the curve, right, and the curve still is on the surface, so it has to satisfy this equation up here, right? Since all these points are on the surface S, they're also on the curve C, right? So effectively we have, this is just a function of t now, as long as we restrict to the curve C. Restrict to the curve C here, right? Okay, so this is true for any t, right? Each t gives you a different point on the curve. Again, we're going to focus on this one particular point here, But this equation here is true for any point on C, on the curve. Okay. And this should be a z here. Right, so what I want to do now is just take the derivative of both sides, right? So essentially I'm going to take f prime of t here, and the derivative of 0 is still 0, right? But for this is a function of another function, right? So we're going to have to use the chain rule here to take the derivative here. And so I'll write it out the usual formal way, right? It's the partial of f with respect to x times the derivative of x plus the partial of f with respect to y times the derivative of y plus the partial of f with respect to z times the derivative of z. Again, all these x, y, and z are with respect to t. So now I'm going to write this a slightly different way here, right? You know that the partial of f with respect to x can be written as f subscript x, right? And then we're, again, at this particular point, x0, y0, z0, right? And then the derivative of x with respect to t, you can also write as just x prime of t, right? Right. So plus the partial of f with respect to y times y prime of t plus the partial of f with respect to z times, z prime of t, right? And this is still equal to the derivative of 0, which is 0. Okay, so far? So now I'm going to get a little creative here, right? This might not look that familiar to you. On the other hand, if you think of the fx, fy, fz, right, you know that that's just the gradient of capital F, right? It's the vector with those three components, right? Also, the x prime, y prime, z prime, we've seen that before. If you think that as a vector, x prime, y prime, z prime, these are the derivatives of x, y, and z. That's just the derivative of r, right? And so what I have here, right, is the sum of the products. If you're clever, you can think of this as a dot product of the gradient of capital F, right? And in particular, at the point x0, y0, z0, right? Dot product with r prime of t. Right? And that's still equal to 0. Okay? So in that light, what do we have here, right? We have a vector r prime of t. Now that is a tangent vector to the curve. So maybe something like this, right? And because it's a tangent vector to the curve, it's also a tangent vector to the surface, right? Okay. What else do we have? Right, we have the gradient. The gradient of f, right? Remember, the gradient points normal to a level curve, but here we have a level surface. So what's normal to the level surface? Something like this, right? It points out of the surface. Or it could point inward, right? That's a possibility here. But let's suppose it points sort of upward or outward, right? So this is, right, this is a normal vector to the surface. This is normal to the surface S. And r prime of t, right, is a tangent vector to the surface S. So what do we know about these two vectors? They're perpendicular. Right? How do I know that? Well, look at the dot product, right? The dot product is 0. That tells me that these two vectors, right, the gradient vector and the derivative of r, right, at this point, are orthogonal. That's the definition of two vectors being orthogonal, is that their dot product equals 0. But in terms of the picture here, that means the vectors are perpendicular. Okay. Now, this was true only for this curve C. However, you can just as well draw a different curve on the surface, right? you can draw this curve, and that's going to have a different tangent vector, a different r prime of c, r prime of t, right? So maybe r2 prime of t, right? But the gradient of f is still going to be normal to the surface. So these two vectors will be perpendicular. That's kind of hard to draw here, but maybe let me do a slightly better job. These are perpendicular, right? And so that's true of any curve, right? So the picture we have down here, let me try to reproduce this. Okay, so here's the surface S, right? Here's my point P, and here is the gradient of capital F at the point P here, right? So at x0, y0, z0, right? And right, for r prime of t, oh, I also drew that with a yellow vector, but let me draw them both in red, right? So you have r prime of t, right, r1 prime of t, and then you might have a different vector, say r2 prime of t, right? And these two vectors point along some curves on the plane, on the surface, Yeah. So, right, so without the curves here, these two vectors, r1 prime and r2 prime, they span a plane. And that plane might look well, it's going to be hard to draw here. Might look something like this, right, at this point, right? So this is a plane, I'll call it pi. I can't use p, right, because we've already used p for, what did we use it for? Oh, the point. Yes, this is p. Okay, so yeah, p is not the plane, p is the point. So we'll say the plane is just pi, right? So notice that the vector gradient of f then is normal to that plane. It's a normal vector to the plane pi. Right. On the other hand, in terms of the surface, it's just touching the surface, right? And it might be easier if I do draw like a sphere. Let's suppose this is our surface S now. Right, so this is S. And let's suppose the point happens to be at the North Pole, right here, right? So imagine a plane that just touches that point. If it helps, right, get a ball, maybe a big one like a basketball, right? If you have a basketball, right, go get it, and get a piece of cardboard, right? And so place the cardboard, this yellow thing, right on top of the basketball, right? So this plane then, this piece of cardboard then, is called a tangent plane. Right? It's tangent to the surface. So that's what pi is, right? So pi is a tangent plane to the surface, right? Right. Now, different points will give you a different surface. If you change p here to a different point, right, you'll get a different tangent plane. Right. So, for example, if I use the South Pole here, I'll get this tangent plane, which is parallel to this plane, but it's not the same plane. Right? It's in a different place. Right? You can also imagine a point on the circumference. I was going to say the circumference on the equator here. If you have a point on the equator, now the tangent plane will be a vertical plane instead of a horizontal plane. Right? So here we have a vertical plane, vertical tangent plane. Right? And then the yellow and the red planes at the North and South Pole, these are horizontal tangent planes. Right? But in general, right, your tangent plane will be somewhere in between. Right? So basically just move that piece of cardboard around the sphere, and at each point of contact with the sphere, you'll get a different tangent plane. Okay, So that's the whole idea of the tangent plane. Again, hard to kind of draw here, but again, think of a basketball, think of a piece of cardboard that you light flat on the sphere, on the ball here, and just kind of move it around, and you get, at each point, you get a different tangent plane. Okay, so I hope that helps. Okay, so here's the definition, right, of the tangent plane. You have a function f that's differentiable at a point P on the surface S, defined, again, implicitly by the equation f equals 0, such that the gradient of f is not the 0 vector, right? Because if the gradient is 0, then you don't get a tangent plane, right? So the plane, which I call pi, right, passing through the point P and normal to the vector gradient of f, right, is called the tangent plane to the surface S at the point P. Right, and then you also have the line passing through P in the direction of the gradient of f, right? That's called the normal line to the surface S at P, right? So since I messed that up, let me draw this one last time, I hope. So here we have some generic surface, right? In fact, let me make it a little more curved so we can see the curviness of it, right? And you have your point P. I'll put it right here in this corner. So that's my point P here, right? So the tangent plane, well, first of all, let's draw the normal vector, something like this. So this is the gradient of capital F at the point P at x0, y0, z0, right? And now the tangent plane will be, well, perpendicular to that. So something like this, right? Just touching at the point P here. Right? Okay. Right, so that's the tangent plane. And then the normal line will be pointing basically along the vector. Right? So this will be the normal line. Right. It points perpendicular to the tangent plane, which is also perpendicular to the surface, right? Right. And keep in mind that if you have a different point, say you have a point way over here, the tangent plane will be very different, right? It'll be a different plane, you'll have a different normal vector, and you'll have a different normal line. So instead of drawing the normal vector, let's just draw the normal line, right? And yeah, we could draw the gradient of f at this point here, say x1, y1, z1. So it's a different point. So point Q here. Okay. So yeah, right. So that's the idea of the tangent plane as well as the normal line. All right. So that's the idea. Hopefully the picture, these pictures here, as sloppy as they are, will give you some intuitive idea. Of course, you can look in the book, and the book has probably better pictures than I can draw here. All right, so let's just do an example. Okay, find the equations of the tangent plane and the normal line, so they want both, to the surface, right? So our surface S is given, again, implicitly by this equation here, right? So this is our capital F, if you will. And our point P is given 2, -1, 1, right? So that's just our x0, y0, z0, right? And this up here, of course, is just f of x, y, z equals 0, right? So how do we find the tangent plane? Well, right, so what do we need to find any plane? We need a point, P, but they give us that. That's given, right? Oh, and you can check that this point P is on the surface. If you plug in x equals -2, y equals -1, and z equals 1, this equation here better be true. So you might want to check that they're not giving you a point that's not on the surface here, right? So let's suppose this surface is, you know, something like this. Well, this is our surface. That point P had better be on the surface. If the point P was up here, some distance away from the surface, then this is not going to work. There's no tangent plane at a point that's not on the surface. Okay. So yeah, it is, and you can check that yourself. But we're looking for the equation of a plane. So you remember the equation of a plane, I hope. If not, you can look it up on your little formula sheet here. Right, so there's the equation. So what do we need? We need a point. We have that. That's the x0, y0, z0. That's given to us. And then we need a, b, and c. So remember what a, b, and c are. Right? A, b, and c are the components of a normal vector. Right? A vector that points perpendicular to the plane. So how do we find that? Well, we have the surface, f, right, capital F, and our normal vector then will just be the gradient of f, right? The gradient will point normal to the surface, and therefore it will point normal to the tangent plane of the surface, right? And of course, maybe we should plug in, of course, the x0, y0, z0, in this case, 2, -1, 1, right? So this point here has coordinates 2, -1, 1. Okay, so that's it, right? So we have our normal vector. In this case, it's given as the gradient, so we have to find the gradient of capital F. Xz cubed. I'm just copying down the equation of the surface again, and we know it equals 0. Yep, now we just take the gradient. Remember, it's a vector at a given point. So what are the components? The components are just the partial derivatives. So take the partial derivative with respect to x. We're going to get z cubed plus 4yz squared, right, plus 0. And then the y partial, the partial of f with respect to y, is just 4xz squared. And then the partial with respect to z, you're going to get 3xz squared plus 8xyz. Right. Yep, so that's the gradient at any point on the surface, but we're only concerned with one point in particular, and that's this point right here. Right? So for that, we'll just plug in, right? So our normal vector n, in fact, you can write it as n here, right? A, b, and c, right? Will just be, the gradient of capital F. And we plug in the x equals 2, y equals -1, z equals 1. And what do we get? So let's see, can I do this all in my head? So 1 cubed plus 4 times -1 times 1. So, yeah, 1 minus 4, I think, is -3. And then 4 times x times e squared. So 4 times 2 times 1 squared is 8. And then the z component will be 3 times x, which is 3 times 2 is 6, times 1. So, and then 8 times 2 times -1 times 1. So I think that's going to be, let's see, this was 6, and then -16. So 6 minus 16 is -10. Yeah, I think that's it. Right? So I think that's my n. Right? So this is my a, b, and c now. So now you just plug all these numbers into the equation of a plane, and you'll get your tangent plane. Right? So we get -3 times x minus x0 is 2, plus b is 8, times y minus y0. Right? Y0 is -1, so y minus -1 is y plus 1. And then c, which is -10, times z minus z0, so just z minus 1. So that equals 0. And there you go. There's the equation of the tangent plane. Of course, this is not the correct format, right? We should multiply all this out. So negative 3x plus 8y minus 10z. And then what are we going to get? Positive 6, positive 8, positive 10 equals 0. So negative 3x plus 8y minus 10 times z plus 24 equals 0. And that looks good. Generally speaking, I like the first number to be positive. So if we just multiply everything by a negative 1, that would be dandy. So you don't have to, but I prefer this version here. Or if you add the 24 to both sides, of course, you can do that as well. Very often I will do that too. Right. So this is the equation of the tangent plane. Okay, so that answers the first question, right? We have the equation of the tangent plane, but they also ask for the normal line. And maybe let's use a different color here for the normal line. So how do we find a line? Well, remember, for a line, we need a point on the line. We have that. That's the same p here. And we need a vector in the direction of the line. Well, what vector would that be? That would be the gradient again, right? So for the parametric equations of the line, and here they are again, it's almost fortuitous that our a, b, and c here are the same a, b, and c that we used for the equation of the plane. Right? That's why we call them a, b, and c, right? So yeah, just plug in the numbers at this point, right? So x is going to be x0, I forgot what that is, that's 2, plus a times t. A is negative 3. Of course, there's nothing magical about these numbers here. If you want to multiply them all by negative 1 and get a vector in the opposite direction, that's fine too. But I guess I'll stick with these numbers here. So 2 minus 3t for x. Y0 is negative 1, negative 1 plus 8 times t for y. And then z will be positive 1 minus 10 times t. So these are the parametric equations of the normal line. Right. Of course, this, you did this back in chapter 11, right? 11.6, I believe. Oh, no, 11.5, I believe it was. But you can also write it, of course, as a vector-valued function at this point, right? So this is just our vector-valued function, our position function for a point on the line. So either way is fine. Either way, these both represent the normal line, the equations of the normal line, right? So you have your tangent plane, you have your normal line, and that answers the question. So very, very reasonable to ask, given the surface, right, like this, find the tangent plane and normal line at a given point. Okay, so let's do another one. This I still write out of the book. I think it's number 8 in the exercises. Find the tangent plane and normal line to z, the surface z equals y over x at the point 1, 2, 2. Okay, so they give us the point, right? That's our point P, if you like. And the surface S is given the usual way, right? As a function of x and y, it's just y over x. Okay, so you have some surface. I'm not even going to pretend to try to draw the surface, right? But suppose this is our surface, S, and we have a given point, and we're looking for the tangent plane at that point, right? So what do we need? We need the gradient vector, right? So here's where it could get a little tricky. You might think, well, okay, take the gradient of this function. But that's not going to work, right? This is the wrong gradient, right? mean, we can do it, but, right, so the partial with respect to x is, I think, negative y over x squared times I. And then the partial with respect to y is just 1 over x times j. So what's wrong with this? Why won't this work? So remember, we need our capital F, not little f. Capital F is a function of x, y, and z. And the gradient of that function, right, will be a vector with 3 components, right? Because it's a vector in space, right? This vector here is a vector in space. It's not on a plane. Well, not necessarily on a plane, right? So the problem with this gradient here is that it only has the 2 components, right? And if you assume that the third component is 0, well, that's a very bad assumption. It's probably not going to be 0 in most cases. And it's definitely not 0 in this case. Yep, so here's the problem, right? This surface is given not implicitly. It's given as an explicit function of x and y in terms of z, right? So you have your z-axis, you have your y-axis, you have your x-axis. So we think of this surface as just the height. Z is the height above the xy plane. Okay. So we've seen those surfaces many times. But for the tangent plane, we insist on it being an implicitly defined surface. Right. So how can we convert from this to this? Yeah, very easily. Very, very easily. Much more easy than going backwards from an implicit surface to an explicit surface. That, first of all, is not always possible. Sometimes you can't do it that way. But from an explicit surface to an implicit surface, it's very easy. Just subtract z from both sides, right? So if you do that, you just get y over x minus z equals 0. So that will be my capital F. Right? Or let's do this in general, right? You just have your f of xy, little f of xy, minus z equals 0. Right? You could do it the other way too. You could do z minus y over x equals 0, but I guess just by default, I would subtract the z from both sides, right? So in this example here, my f of xy is just y divided by x minus z equals 0. So this is the thing that you're taking the gradient of, right? Now we can take the gradient of capital F, right? And you can see the partial with respect to x, right, is still going to be negative y over x squared times I. And then with respect to y, you just get plus 1 over x times j. And now the gradient, or rather the partial derivative with respect to z is just negative 1 times k. And in fact, it's always going to be negative 1. If you subtract z, then the derivative, right, of negative z is just negative 1. Okay, so you can see it's similar to the gradient of little f up here, but you're forgetting the minus k, right? And of course, that's not going to happen when you have a function of just x and y. Okay, so be careful. If you're given a function of x and y as a surface, you have to convert to the implicit form by just subtracting the z from both sides, and then using that as your implicit function, f as a function of x, y, and z. So that gives you your surface implicitly. Right. So now we're almost done. Now we just need the normal vector, and the normal vector is the gradient at the specific x, y, and z, and I forgot what those are. 1, 2, 2. Right. So way up here, x is 1, y is 2, z is 2, right? So when you plug those into the gradient, you just get negative 2 over 1 squared times I, plus 1 over 1 times j, minus 1 times k. So that's just the vector with components, negative 2, 1, negative 1. And again, that's just the a, b, and c. Now we can find the equation of the plane. Yep, remember the point was 1, 2, 2, right? Yeah, 1, 2, 2, right? So this is my x0, y0, z0. And so now you just write down the equation of the plane. Here it is one more time. So hopefully not hard to forget at this point. So now plugging in the numbers, we get negative 2 times x minus 1 plus 1 times y minus 2 plus negative 1, we should just do minus 1, times z minus 2, yep, equals 0. So as usual, multiply it all out. And then we get 2 minus 2 is 0, and then plus 2. Right? Again, I like to multiply by negative 1. So that should give you positive 2x minus y plus z minus 2 equals 0, which is fine. Or add the 2 to both sides. And that works too. So this is the equation of the tangent plane. To this surface, z equals y over x at the point 1, 2, 2. Right. Oh, don't forget about the normal line. I almost forgot the normal line here. Yeah, actually the book didn't ask for that, but that's almost as easy, right? So I'm going to write it as a vector valued function this time, right? So that's just x0 plus at, and then y0 plus bt for the second component, and then the third component is z0 plus ct. So the equation of the normal line as a vector function, right, is just going to be, I forgot the, yeah, so 1, 2, 2, right? So 1, well, I could use the plus, but let's use the original a, b, and c, right? So 1 minus 2t, and then 2 plus 1t, and then 2 minus 1t. So there you go, right? So this will be our normal line. Right. Right. And remember, this is not unique. Obviously, right, if you had an answer of 1 plus 2t, 2 minus t, and then 2 plus t, that's just as good. That's just as good, right? It's your vector, right? You're just moving along a line, right? And whether your vector is pointing this way or this way doesn't matter, right? If you just change the vector to its opposite, so instead of u, you use negative u, or I should use v here, right? So v or negative v doesn't matter. So like I say, the parametric equations of the line are not unique. And I should have mentioned that in the previous example as well, that, you can have many different answers here, and that they're all correct, right? Not quite true for the plane. I mean, you can convert them from one form to another, right? Whether you put the d on the left or on the right doesn't matter. And, you can multiply all these by any non-zero number, right? So your answer might be, 6x plus 3y. Oh, wait a minute. If this is, yeah, this should be a minus y here. I don't know why I changed that to a plus. Yes, minus y. Oops. Right? And then plus z. Okay, good. Now they're both correct, right? So yeah, so this is not a plus 3y, it's a minus 3y. Right. So yeah, minus 3y, and then plus 3z equals 6. So same plane, no different. I just multiplied everything by 3. Right. I mean, you can multiply everything by 10 or 217 if you want. But, if you can divide by a common, common multiple here, then I would do that. I would make it as simple as possible. So, right. So it is true that there are many different equations of the plane that has the same, that represents the same plane. And that's also true for the normal line as well. Okay. Anyways, so two pretty routine examples. This example was a little trickier if you didn't, right, convert the function to an implicit surface, and you tried using this gradient as your a, b, and c. The problem is there is no c here, so that would not work. That would not give you the correct equation of the tangent plane. Okay, so a definition, the angle of inclination of a plane, and let's suppose it's given by this equation here, is the angle theta, and theta is just the inverse cosine of the absolute value of n dot k divided by the magnitude of n. So, right, n, of course, is your normal vector, right? It's the vector with components a, b, and c. Right? And so the magnitude of n, of course, is just the square root of a squared plus b squared plus c squared. So we could have written it in terms of that, but I think this should make more sense. Well, okay, let's write it that way. It's also the inverse cosine, or the arc cosine of, so n dot k is really just c, right? C could be negative, so absolute value of c, divided by the square root of a squared plus b squared plus c squared. I don't remember it that way. I remember it this way, but either way is correct, right? Right. So okay. So what do we mean by the angle of inclination, right? So let's suppose we have our XYZ plane here. This is the x-axis. I kind of missed here, so let's try it this way. Here's our y-axis. Right. Yep. So yeah, this is our xy plane. Right. Now suppose I have a different plane. Right. Let's suppose the plane given by this equation might look like this. Right. So this plane is, you can think of it as being tilted, right? This plane is tilted, right, in this direction here, and it's tilted by some angle. This angle here, right? This is our theta, right? So, right, so that is our angle of inclination, right? And so how do we find that angle? Well, let's start with the normal vector n. So that's going to be normal to this plane here. You know what? Let me draw it over here because it's interfering with the z-axis. So here's the normal vector n, right? And let's draw the unit vector k. K, of course, is just points in the vertical direction, right? So yep, so the angle theta is the same as this angle here. It's the angle between n and k. And if you remember, how do you find the angle between two vectors? It's just this formula, right? So this is nothing new. This came from, this came from chapter 11. The angle between two vectors, n and k, right, is this angle, right? Now, it's just tilted, 90 degrees. So in other words, right, if this is your, oh, sorry, that would be your angle that's in the k direction, right? And then the angle n, or the vector n, would be pointing this way, right? And so you get the same angle, right? So just rotate this 90 degrees, right, pi over 2, and you have the same picture. So there you go, right? This is the formula for the angle of inclination, and that's all it is. So maybe we should do a quick example. So quick example here. So let's find the angle of inclination, theta. So find theta for the plane, 7x minus 2y minus 3z equals 12. Right? So So obviously my n is just 7, -2, -3. I'm going to need the magnitude of that vector, so take the norm of n, take the norm of that vector, and so that's going to be, let's see, so 49 plus 13 is 62, so square root of 62, that sounds familiar. We had an example like that not too long ago. 12. Yeah, 62. Okay. And then, so the dot product with k, if I take n dot k, right? Oh, let's write it out. I was going to do this. I was going to do this in my head, but right. Remember, k is just 0, 0, 1. So you're just going to get -3. Right? 0 plus 0 minus 3. Right. But remember, you got to right. We want this to be a positive, right? The angle of inclination should be an acute angle. Right? It should be less than 90 degrees. So yeah, if we use the -3 here in the numerator, that will give us an obtuse angle. It'll be bigger than 90 degrees, right? So yep, so the cosine of theta is just going to be, again, absolute value of n dot k over the magnitude of n, right? So in this case, it's the absolute value of -3 divided by the square root of 62, which is 3 over the square root of 62. So the angle of inclination then is just the arc cosine, or inverse cosine, of 3 over the square root of 62. And you can just use your calculator. We'll use degrees as usual here. Yep. So I get about 67.6 degrees. 0.60 degrees. So you have the exact and you have the approximate. Just make sure you know how to do both. Yeah, I think that's it. So a very easy example. Okay, I guess we're ready for another example. All right. Find any points on the surface. Z is equal to 4x squared plus 4xy minus 2y squared plus 8x minus 5y minus 4. And again, this surface may not be familiar, but I'm pretty sure it's, oh, it's not a paraboloid. I think it might be a hyperboloid. I'm not sure. Doesn't matter, right? It's just some surface. So find any points on that surface at which the tangent plane is horizontal. Okay. So, right, so whatever your surface looks like, right? Where will the tangent plane be horizontal? Probably not here, right? Probably not over here. Maybe somewhere at the top, right? Here the tangent plane will be horizontal. Okay, so if it has such a point, what happens at that point? Or in particular, think about what happens to the normal vector. The normal vector will be vertical, right? In other words, it'll only have a z component. So remember that the normal vector will be the gradient of capital F. And so we want to know, right, where that gradient, right, has a vector, is a vector with whose components are going to be 0, 0, and then some number for the vertical component, right? So there you go, right? So we need to take the surface, take the gradient, and then figure out where that gradient, that gradient is 0, 0, whatever, right? Z, C, right? So where A and B are both 0, right? I mean, C could be positive or negative, right? It can be pointing downward too, but just upward or downward, right? So, yep, here's the surface again, and I don't know why I'm copying it down, because remember, you're not taking the gradient of that, right? You have to write it in terms of capital F. So the way I'm going to do it is I'm just going to subtract z from both sides. So I have to write all this down again. minus z, and that's what equals 0. So now you can take the gradient and I'll use ij and k this time, right? So the I component, or x component, will be 8x plus 4y plus 8, right, times I. The j component, or the y component, will be 4x minus 4y minus 5. And then the z partial derivative will be just negative 1, right? So there you go, right? There's our gradient. And we want to know, the question is, right, when does it equal a vector 0i plus 0j plus c times k? And in this case, our c just happens to be negative 1, but it could be any number, right? So just match them up, right? The first component gives you this equation, right? And the second component here gives you this equation. It's supposed to be 4 minus 5 equals 0. So you have two equations in two variables. This is nothing new. You just solve this system of equations, and that'll give you your x and y, I think, right? In fact, this is set up perfectly, right? Let's just add the two equations together. 8x plus 4x is 12x. 4y minus 4y is 0. And 8 minus 5 is 3. So this tells me that x is negative 3 over 12, or negative 1/4. Okay. But now we have to find y, right? So can we use this equation here? 4 times negative 1/4 is negative 1, minus 4y minus 5 equals 0. So this tells me that negative 4y equals positive 6, which tells me that y is negative 3 over 2. Okay, so yep, let's just write it down here. Y is negative 3 over 2, right? Okay, so that should do it. That gives us a point, right? A point on the surface. Hang on, this is a surface in space, right? A point is not just an x and a y. It's also a z. All we found were x and y. How do we find z? Yep. Go back to the original equation, right? Just plug in your x and y's and then solve for z. Okay. So, yep, z was, oh, should I just copy it all down again? Oops. Yep. Okay, here we go, right? So our z coordinate then for the point on the surface, that's where the tangent plane is horizontal, is just going to be, so 4 times 1 over 16 is 1 over 4. This is going to be negative 1 times negative 3 over 2, so that's plus 3 over 2, minus 2 times 9 over 4, so minus 9 over 2, and then minus 2, and then, wow, plus 15 over 2, minus 4. Yeah, just go to your calculator. I just don't feel like doing that by hand. Okay, so my calculator gives me negative 5 over 4. Okay, so to answer the question, right, the question is find the points on the surface, and there's only one here, right? There was only one solution, so there's only going to be one point. So that point has coordinates negative 1 over 4, negative 3 over 2, and negative 5 over 4. So that is the one point on the surface where the tangent plane is horizontal. Right. Okay, so yeah, the tangent plane is horizontal when the normal vector to the plane, right, only has a vertical component, right? So the x and y components are zeros. And that gives you two equations, two variables, solve that system, and in this case you just get the one point on the surface. And then a theorem which at this point I hope is more or less obvious, because we've been using it all the time here, that when you have a surface, right, given, again, let's say given implicitly, f of x, y, and z equals 0, is a, right, it defines an implicit surface, right, say S at a given point, right, that if you take the gradient of f, as long as it's not the 0 vector, the gradient of f, right, at a specific point, x0, y0, z0, which is right here, right, that gradient points normal to the level surface, right? So this just, just says what we've been saying all along here, that the gradient is normal to the surface, right? Very similar to what we did in the last video where we had level curves, right? Where we had our level curve, and we said that the gradient points, right, little f now, the gradient, points normal to the curve, or perpendicular to the curve, right? It doesn't have to point outward, it can point inward too, but yeah, I guess it depends on how the function is defined. But all these vectors are normal to the curve, so, right, all these gradient vectors will be perpendicular to the surface. Okay? Yep. So, quick example of that. Suppose we have a sphere. That's a pretty easy surface, right? So x squared plus y squared plus z squared is equal to 49, right? And we want to find a vector perpendicular to the surface, right? So find a normal vector. To the surface, right? So that's easy enough, right? You just find your capital F is x squared plus y squared plus z squared. And to make it equal to 0, right, because we've always said it equals 0, subtract the 49 from both sides. That really doesn't matter that much. So take the gradient, and that will be normal to the sphere. So the gradient here is just 2x, 2y, and then 2z. Right? And in fact, the 2 doesn't really matter. That just gives you the magnitude of that vector, right? But if all you need is any vector, you can divide by 2 here, right? So you have your sphere, right? And notice that it's centered at the origin, right? So the origin 0, 0, 0 is the center of the sphere. So we have our equator. Right? And now it should be pretty obvious that, right, at a given point on the sphere, your normal vector n, or the gradient of capital F here, points in a direction that's outward, right? Right? If I just move that vector to the origin, so that the initial point is the origin, of course you just get a vector, right? A position vector, x, y, z. So, yep, if your point is over here, right, it still points normal to the surface, right? If you're on the equator, it points outward this way. If you're in the southern hemisphere, it'll point downward. Oops, sorry. Let me fix that. Right. If you're at the North Pole, it points directly upward. South Pole points directly downward. You get the idea, right? So all these vectors point outward. Right. It just depends on what you use for your x, y, and z, of course. Right. So different points on the sphere will give you different normal vectors. Okay. Yeah, so the sphere is a level surface for the function, right, y, x squared plus y squared plus z squared. I'm being a little sloppy here, right? right? So yeah, this is just a function, right? It's the square of the distance from the origin. And if the square of the distance from the origin is a specific value, right? In this case, 49, that gives you a level surface. Right? Different radii, right? A different radius will give you a different level surface. So yeah, they're all spheres, concentric spheres, right? Because the center is the origin, but they all have different radii. But that doesn't change the normal vectors. The normal vectors would all be basically perpendicular to each of these surfaces. So that's all this theorem really says. All right, I think we have time for one or two more examples, right? And this I just stole right out of the book. Show that the surfaces are tangent to each other at the given point, right? The point is 2, 3, negative 3, by showing that the surfaces have the same tangent plane at that point. Okay, right, so we're given two surfaces, and more or less they're already implicit surfaces, right? So let's suppose the first surface, we'll just call that capital F. And it's defined by the equation, right? X squared plus y squared plus z squared minus 8x minus 12y plus 4z plus 42 equals 0. So this is a sphere. This is the equation of a sphere. It's just not centered at the origin, right? So the center might be some other point. And I should be able to do this, right? I think the center is the point 4, 6, negative 2, but don't quote me on that. Right? You just have to complete the square. Okay, so it doesn't matter, right? It's just some sphere. And maybe we can draw the sphere here. Right, so something like this. Just realize that the center is not the origin anymore. The center is that point that I just erased, right? Okay, right, and then we have another surface. I'll call it capital G. And it's given by this equation, x squared plus y squared plus 2z. And then just to be consistent, how about minus 7 equals 0? And this is a paraboloid. Okay. Again, you don't really need to know that to solve the problem, but it does help because, right, what's going to happen here is that, right, at some point we want to show that the sphere and the paraboloid are tangent to each other, so they just touch each other, right? So this might be the paraboloid facing downward here, and at this point here, I'll do this point in yellow, right there's where they touch. So that should be the point 2, 3, negative 3, right? So first of all, we should check that this point is on both the sphere and the paraboloid. Right? In other words, what we have to check is that if I plug in 2, 3, negative 3 into F, I really do get 0. And do the same thing for G. Plug those in and make sure this equals 0 here. Okay, so I'm going to let you do that because that's just basic math. Just plug in the numbers and see if it's 0. Right? So that's right. So that just tells us that the point is a point that's common to both the sphere and the paraboloid. Right. Right. On the other hand, that doesn't mean that they're tangent to each other. Right? So the tangent plane will be, well, in this picture, it looks like the tangent plane will be horizontal because it's sitting right between the sphere and the paraboloid. Or, yeah, think of this as the plane coming right out of the board at you here, right? Yeah. Right? So that's the tangent plane right there. I'm drawing it horizontally. I don't know that it is. I'm pretty sure it is. But we'll determine that later, right? So basically just find the equation of the tangent plane right, to the sphere and then to the paraboloid, and we'll see if it's the same plane, right? So how do you find the tangent plane to the first surface, the sphere? So let's do the sphere first. Well, what do we need? We need a point. They give that to us, right? And we need a normal vector. So that's just the gradient of f. So without further ado, the gradient at this point is just the vector with the components that are partial derivatives. So 2x minus 8, 2y minus 12, and 2z plus 4. Right. Now, to get the actual normal vector at that point, right, now we have to plug in the 2, 3, and negative 3. So that's going to be 4 minus 8, negative 4. 6 minus 12 is negative 6. And then negative 6 plus 4 is negative 2. Okay. So there's our normal vector. And if you want to find the equation of the plane, go right ahead. It turns out we don't really need the equation of the tangent plane. Right, so now let's do the same thing for the surface G, the paraboloid. So take the gradient of G, and that's a little bit easier, right? That's just going to be 2x, 2y, and 2. So plug in the same point, 2, 3, negative 3, and we get 4, 6, 2. I'm sorry, 4, 6, 2. Now, you might say, wait a minute, that's not what we got up here, right? These vectors are not equal. So how can we say that they have the same tangent plane? I never said that the normal vectors have to be equal, right? The tangent plane has to be equal, has to be the same plane for both of them, but not the normal vectors, right? So imagine, if you will, if this red line here is actually the tangent plane, think about the normal vector to f, and I think I have it right up here. It's going to point downward. So it's not, okay, so I drew the wrong picture here. It's not going to be straight up and down, right? But one of them is going to be kind of downward, the other one will be kind of upward, right? So yes, they're just opposite, right? This is negative n, this is positive n. Or, yeah, either way, right? So the picture might be a little bit off here. So if you want me to fix that, great. So here's the sphere again. And the paraboloid then might be somewhere over here, right? So it's at this point where they meet, where they're tangents. And then this would be the tangent plane, right? It's kind of hard to visualize here, but right, you have to imagine that it's the plane right in between these two, right? Yeah, a lot easier up here, right? Or, yeah, maybe I think I can fix that. Imagine this is the paraboloid. I don't think it is, but that's close enough, right? So, yeah, in this case, the tangent plane will be this, right? And this point of intersection here, this point is still, right, 2, 3, negative 3. Okay, so that should give you the picture here. Right? So yes, as long as these two vectors, they don't have to be equal, but they have to be parallel, right? And they're certainly parallel. They're certainly parallel vectors, right? Just multiply 1 by negative 1. Right? So yeah, let's do that, right? So the gradient of G at the point 2, 3, negative 3, right, is just the opposite, negative 1 times the gradient of f at the same point, 2, 3, negative 3. Right. So that's what it means to be parallel. One is a constant multiple of another, right? Remember, two vectors are parallel, right? U and V are parallel if U equals C times V for some constant C. In this case, C is negative 1. Right? So, yep, so that does it. They have the same tangent plane. Oh, and what is that tangent plane? Well, now you can just find the equation of that plane very easily. And multiplying it all out, so negative 8 minus 18 plus 6. So, yeah, negative 26 plus 6 is negative 20. And why don't we just divide by 2? And then add the 10 to both sides, right? So that is the common tangent plane to both surfaces. They both have the same tangent plane. And it's this red plane here. I know it looks like a line, but keep in mind that, right, I'm squashing this down into 2 dimensions. So here's the sphere squashed into 2 dimensions. Here's the parabola squashed into 2 dimensions. So it looks like a parabola. Yeah, it looks like a parabola. And so then it looks like they have a common tangent line. But, you know, if you do this in 3 dimensions, it's a tangent plane. Okay. So, yeah, not a hard question, just one that you have to, you know, understand, you know, how do you find a tangent plane to a surface? How do you find a tangent plane to a different surface? And if that's where the surfaces intersect, they have that common point of intersection, you just have to show that they have the same tangent plane. And this is the same tangent plane for both surfaces at the same point, 2, 3, negative 3. So yeah, that should do it. I hope that helps.